In this work, we study the problem of using Imperial transfer for tasks that require simultaneously wide task space generalization and sub-millimeter accuracy in the control. In order to achieve this, we develop and present a novel Coarse-to-Fine controller for Sim2Real. It initially uses classical motion planning based on ICP pose estimation in order to get to a point just above the object of interest known as the bottleneck pose. It then switches to an end-to-end neural network-based controller that maps images from the wrist-mounted camera directly to actions in order to complete the task. We train our network entirely in simulation using domain randomization. Putting all this together, we show that we can obtain a controller that generalizes across a wide task space whilst also achieving sub-millimeter precision in the control, all without using a single real-world training data point. We also test our method on more complex multi-stage control requirements with a screw motion task that requires a twisting motion after the correct positioning of the irregularly shaped ring. Finally, we find that our controller is robust to hard lighting conditions and distractor objects. As our baselines, we test two natural alternatives, both of which struggle to complete the tasks with the specified requirements. First, this clip shows a fully end-to-end controller that uses a neural network in order to complete the full task. Then, this clip shows a fully planning-based controller that uses ICP registration for its state estimation. Finally, as part of this work, we also conducted a set of studies on the Sim2Real transfer aspect of our framework. These investigate the influence of the input modality used as our neural network inputs and of the network architecture and image representation used. We focus these studies on the fine controller, using incrementally more challenging insertion tasks in order to assess the performance. We found that firstly, using RGB-based control worked better than both stereo IR and depth, and secondly, that end-to-end controllers using key point-based network architectures outperform regular CNNs.